She hasn't responded yet. Oh. We do a quick test. All right. Testing. Okay, according to this. According to this, things are working from my end. I don't know about her. So I'm just going to continue to discuss elemental analysis. In some textbooks, they call this combustion analysis. Same thing. So we talked about percent composition earlier, and we talked about how we can determine the empirical and molecular formula based on percent composition data, right? So now we'll be looking at how we actually, in practice, determine the percentages. Now, this discussion will be limited to organic compounds. And when we talk about organic compounds, in this context, So yeah, in this discussion, we'll be limited to organic compounds, and we're talking about basically compounds of carbon. And organic chemistry is a separate broad category by itself, and it deals mainly with compounds of carbon. And typically, a typical organic compound will contain carbon and hydrogen, and in a lot of cases, oxygen and other elements like nitrogen, sulfur, and so on. So these are the kind of compounds we'll be talking about in reference to the type of elemental analysis we'll be looking at today. Now, the thing about organic compounds, what's going on here, is that when you expose them to a flame, like if you have a compound in, let's say, a spoon or, whatever, and you heat it until it starts burning, then basically you can rest assured that two of the compounds or products of the burning or combustion will be carbon dioxide and water. Now, there may be other substances based on other elements being present, but basically it's a carbon dioxide and water that we actually use to figure out, in addition to other things we use to figure out the composition of the organic compound, right? So in this method, we burn the substance in oxygen, right? And the products of the combustion, which are usually carbon dioxide and water, are isolated and weighed. And then based on those masses, we can work backwards to determine the mass of each element that is present in the original compound. All right, so that's pretty much the basis for this sort of analysis. And the next slide gives you a schematic representation of the apparatus that is used for this sort of elemental analysis. So as you can see, we have a series of compartments here. You have 3 separate compartments, right? The first one will contain the sample of the substance that you're analyzing, all right? And you see here, oxygen is being rushed into it. And this is actually a furnace, so this will be heating, right? So when you heat it, of course, the products of the combustion will be more than likely carbon dioxide and water. As I said before, there may be other substances depending on the composition, but carbon dioxide and water definitely would be the products of this combustion, right? So we have to ensure that this sample here is completely burnt in order for this to work. You want to get all of this converted to carbon dioxide and water, and then those gases will be led into the other compartment. Now, in this compartment, you have a substance here known as magnesium perchlorate, and its role is to absorb the water that is produced as a result of the combustion here, right? So the way this is done is that before you start everything, you weigh the magnesium perchlorate, right? And then you do the burning, and then this absorbs water, and then you weigh it again, right? And difference between the initial mass and the mass after absorption of water would obviously be equal to the mass of the water, right? One precaution that you'd have to take in this setup is that you have to ensure that you have enough magnesium perchlorate there to absorb the water that is produced, all right? So once we are sure of that, and we are sure that all the water is absorbed by the magnesium perchlorate, then the only thing that should be emerging from this compartment would be the carbon dioxide, and that is led into this compartment, which contains sodium hydroxide. This could also be potassium hydroxide as well. In either case, the role of the sodium or potassium hydroxide is to absorb the carbon dioxide, right? So again, as we described here, what we would do is weigh the sodium hydroxide before and then weigh it after. The difference in masses would give you the mass of the carbon dioxide that is produced, right? So now that we get the values for the masses of the water and the carbon dioxide, then we can use those values to determine the empirical formula for the organic compound, all right? So this is basically the setup that is used to carry out a combustion analysis. Now, the next slide is basically giving you, a diagram which shows you what happens when you burn methanol, which is an organic compound, right? So basically, this is really looking at the microscopic level of things. We have two methanol molecules here reacting with excess oxygen to form carbon dioxide and water, and you might have some excess unreacted oxygen, right? So basically, the methanol here, right, contains the carbon and hydrogens and one oxygen atom each. And basically, the carbon here and here ends up in the carbon dioxide, right? So whatever the mass of the carbon that you end up with in the product here would be the mass of the carbon that you started off in the original methanol, right? As far as the hydrogens are concerned, we have these hydrogens here bonded to the carbon, and these hydrogens end up being bonded to oxygens here. So if we can figure out the mass of hydrogen present in the water molecules, then we can basically assume that it will be the same mass of hydrogen that is present in the original methanol molecule, all right? And if you know the original mass of the compound here, and we figure out the masses of the carbon and oxygens, and hydrogens, I'm sorry, then we can figure out the mass of the oxygen by simple arithmetic, all right? So that's basically what is involved when it comes to elemental analysis. Now, what I'm going to do next is an actual example, a typical elemental analysis question, right? It says burning 0.1000 gram sample of a carbon, hydrogen, and oxygen compound in oxygen yields 0.1953 grams of carbon dioxide and 0.1000 grams of water. And then it says a separate experiment shows that the molecular mass of the compound is 90 AMU. So the question is asking for you to determine A, the mass percent composition, B, the empirical formula, and C, the molecular formula of the compound, all right? So I'm going to need some space for this. So what I'm going to do is take this over here and bring up, I will use Word. Word seems to be pretty reliable for these purposes. Okay, so the question says, you're starting with a compound. The compound contains carbon, hydrogen, and oxygen, right? So carbon, hydrogen, and oxygen. We don't know what the formula is yet, but we know that these are the different elements that make up this compound. It reacts with oxygen and it forms carbon dioxide and water, right? Now the question says that you're starting off with 0.100 grams of the organic compound, and it says that the mass of the carbon dioxide produced is 0.1953 grams, and the mass of the water produced is 0.100 grams, all right? So those are the masses. Hold on 1 minute. Forgot to share my screen just in case. Oh, she dropped out. All right, what I'm gonna do is still share my screen. Okay. All right, so this is basically what you're given. And the first part, A, you're asked to find the percent composition, all right, of each element. So how are we going to do that? Well, as I said before, if we know the mass of carbon present in carbon dioxide produced, that would be equal to the mass of carbon present in the original organic compound. So what I'm going to do is, I'm going to start off with the 0.1953 grams of CO2, and the aim is to find the mass in grams of carbon present. So the way we're going to do that is 0.1953 grams of carbon dioxide. And the first thing I'm going to do is convert it to moles, right? So I'm going to put 1 mole of carbon dioxide above, and down here will be the molar mass of carbon, which is actually equal to 44.01 grams of carbon dioxide. We get that, of course, by adding up the molar masses of the 2 oxygens and 1 carbon in the formula, right? So the grams of carbon dioxide will cancel out. And the next step now is to find the mole ratio between the carbon dioxide and carbon present. And based on the formula, we can say that 1 mole of carbon dioxide will contain 1 mole of carbon. And then the final step is to convert the moles of carbon to grams of carbon. And that would be done by multiplying 12.01 grams of carbon over 1 mole of carbon, all right? So that will give us the mass of carbon present in the original compound, which is also present in the carbon dioxide. So let's do the math and see what this gives. So that would be 0.1953 divided by 44.01 times 12.01. And according to my calculations, this works out to be equal to 0.053 grams of carbon, all right? So that's basically how that is done. Then we have to do something similar with respect to the hydrogen. Now, according to the question, the mass of water that is produced is 0.100 grams H2O, and we need to find the mass of hydrogen present in the water, right? So we start off with 0.100 grams of H2O. We convert that to moles. So you're going to have 1 mole of H2O above as a numerator. And down here would be the molar mass of water, which is equal to 18.02 grams of H2O, right? Again, we get that by adding up the molar masses of all the elements in the formula. And then now, here's where students tend to make a crucial mistake when they're doing problems of this type. Here, if you remember here, we said that for every 1 mole of carbon dioxide, there's 1 mole of carbon, right? Well, in the case of water, because you have 2 molecules, or I should say 2 atoms of hydrogen for every 1 molecule of water, the conversion factor that you're going to use here is 1 mole of H2O down here, and above you're going to have 2 moles of hydrogen, right? This is a very common error that students make. They tend to use 1 here instead of 2. So please remember that, all right? And then the last step is similar to the last step that we did before, where we convert the moles of hydrogen to grams of hydrogen. And to achieve that, we're going to put 1 mole of hydrogen down here and 1.008 grams of hydrogen above. And then we work this out. So I forgot to add an extra 0 here and here. Okay, so that's 0.1 divided by 18.02 times 2 times 1.008. And according to my calculations, this works out to be equal to 0.01119 grams of hydrogen, all right? So far, we have successfully calculated the masses of hydrogen and carbon. But remember, the compound contains carbon, hydrogen, and oxygen. So now we need to find the mass of oxygen. And that's very easy because they gave us a total mass, right? So basically all we have to do is take the total mass. So let me write here, mass of oxygen will be equal to the total mass of the compound, which is 0.1000 grams, and subtract from that the sum of the mass of carbon and the mass of hydrogen, which would be 0.05330 grams plus 0.01119 grams. And whatever that gives, that should give us the mass of oxygen. So let me do that now. 0.1000 minus 0.05330 plus 0.01119. So according to my calculations, this works out to be equal to, and please check, do these calculations along with me because I could be totally wrong in my calculation here, but this is what I got. I got 0.0, let me see, 4 decimal places. Okay, so 0.0355 grams of oxygen, all right? So now that we have the masses of each of these, we can determine the composition. I'm going to need some space, so let me erase up here. In fact, let me erase this. Let me erase all this here. Okay. So to find the percentage of each of them, let me start off with the percentage of carbon. That will be equal to 0.05330 grams divided by the total mass, which is 0.1000 grams times 100%. And that will be equal to 53.30%. Percentage of hydrogen would be equal to 0.01119 grams divided by the total mass again, times 100%. And that will be equal to 11.19%. And then I'm going to need some more space again. And then for the oxygen, the percent of oxygen would be equal to 0.0355 grams divided by 100 grams times 100%. And that would be equal to 35.5%. And that's basically how you solve the A part. And you can check to see that they add up to 100%. Let me do that now. So 53.30 plus 11.19 plus 35.5, 99.999, or 99.99. So close enough, all right? So that's basically how the A part is done, all right? Any questions about this? Any questions? Any questions? All right, so that was the A part. Now the B part says you have to determine the empirical formula. Now, there are 2 ways you can do that based on what we have done before. You can determine the empirical formula by using the percentages that we just calculated here, or you can determine the empirical formula by using the masses of the carbon, hydrogen, and oxygen. It doesn't really matter which one, all right? So what I'm going to do is I'm just going to use the percentages since we have them here. Might as well, right? So let me, okay, let me erase this here. Whoops, not that. I want to erase the top part. And I'm going to do the same thing as I did previously when determining the empirical formula in the other examples that we looked at. I'm going to construct a table so you may remember the steps involved in that. So at the top of the table, I'm going to have carbon, hydrogen, and oxygen, and the first row will contain the masses. So since I've decided to use the percentages, I'm going to express the masses in terms of the number representing the percentages. For carbon, that was 53.30%. For hydrogen, that was 11.19%. I'm sorry, not percent, grams, my bad. Because I'm assuming that we're working with 100 grams of the compound. And then in the case of oxygen, that's 35.5 grams, all right? So those are the masses. Now, do you remember what the next step is? Based on the previous examples that we did last class.
You take that number
Mm-hmm.
and then you multiply it by the 1 mole on top and then the mass,
The molar mass.
the molar mass, yes. 30.
Right, we do that for each case. And the purpose of that is to determine the moles in each case, right? So in the case of carbon, that's 53.30 grams multiplied by 1 mole over 12.01 grams. In the case of hydrogen, that's 11.19 grams multiplied by 1 mole over 1.008 grams. And in the case of oxygen, we take the 35.5 grams and we multiply by 1 mole over 16.00 grams. So we have to work out each of these. Let me just erase what's down here. Okay, so in the case of carbon, that's 53.30 divided by 12.01. And I got 4 many 6 weeks? 4 6 weeks. So 4.438 moles. In the case of hydrogen, divided by 1.008, I got 11.10 moles. And finally, in the case of oxygen, that's 35.5 divided by 16. So I got, in this case, 2.22 moles. All right? Okay, what's the next step?
The least amount of moles.
Right.
And divide that.
You divide everything by the lowest number of moles, which would be, in this case, the oxygen, the 2.2. So this would be 4.438 moles divided by 2.22 moles. In the case of hydrogen, that's 11.10 moles divided by 2.22 moles. And this will give you 1, right? So let's see what these two would give. So 4.438 divided by 2.22. And according to this here, this rounds off to basically 2.00. And in the case of hydrogen, that's 11.10 divided by 2.22. And I got basically 5.00, and that's 1. So therefore, the empirical formula is C2H5O. All right? And that's what that is done. And then the C part says calculate the molecular formula for the compound. So in order for us to do that, we need the empirical mass. So the empirical mass would be the molar mass of the empirical formula, basically, right? So that's 2 times 12.01 plus 5 times 1.008 plus 16 So according to my calculation, this works out to be equal to 46.03 grams per mole. Now, according to the question, hold on. According to the question, what do you call it? The molecular mass is 90 AMU. So basically, that means that the molar mass is equal to 90 grams per mole. So therefore, the integral factor would be 90 grams per mole divided by 46.03 grams per mole. So 90 divided by 46.03. And this is equal to basically approximately 2. All right. So what does that mean? That means that the molecular formula is equal to C2H5O multiplied by 2, which is the same thing as C4H10O2. All right. And that's basically it. So that's a typical combination of combustion analysis question along with determining empirical and molecular formula and all that good stuff. All right. Okay, any questions about this example? Any questions? All right, so moving along. Okay, so now we're going to talk about equations, and this should be a review for you guys. We all know what chemical equations represent. It's basically a shorthand way of describing what happens in a reaction in terms of reactants and products, all right? And also it gives you information about the state of the different substances and the reaction conditions in some cases, and also about the relative amounts of the reactants and products involved in a chemical reaction, right? So of course we know that in any chemical equation, we have the reactants on the left, the products on the right, the arrow pointing from left to right, and we have state symbols such as S for solid, G for gas, L for liquids, and AQ for aqueous solutions, right? In some cases, you might see something like a triangle above or below the arrow. That basically means that you're heating the reactants to make the reaction go. And in some cases, even more specific information is given, like the actual temperature, the actual pressure, whether or not a catalyst is involved, and so on, all right? So those are just some things that you will see in any chemical equation. Now, of course, the chemical equation has to be very accurately representing the quantitative relationships between the different substances involved. And this is based, of course, on the conservation of mass law, which says that matter cannot be created nor destroyed. And according to Dalton, according to his theory, which explains that in any chemical reaction, atoms are not created nor destroyed. So basically what that means is that the same number of atoms of each element that is present among the reactants must be the same for those elements among the products, right? So therefore, in order for the equation to accurately represent all of that, we have to make sure that the equation is balanced. So just to give an example, and again, this is something you guys should already know about. We have this equation here, H2 plus O2 to give you H2O. Now, this equation, as it is not balanced. Why? Because if you look at it carefully, even though you have 2 hydrogen atoms here and 2 here, but you have only 1 oxygen atom here and 2 here. So just by virtue of the fact that the oxygens are not balanced, the equation is not balanced. Now, there are incorrect ways of balancing it, and there is a correct way of balancing it. Now, what this is showing you here are 2 incorrect ways, right? You cannot simply add the deficient atom to one side just like this, right? That's a no-no. Another thing you can do is change the formula of any substance by changing the subscript, such as what is done here. Can't do that, right? The correct thing you need to do is make adjustments to the coefficients. The coefficients are the numbers that are placed in front of the formulas of the different substances. So in practice, what you do is, nope, wrong one. What you do is make changes to the coefficients, such as in this case here, because I know that there are 2 oxygens here and 1 here, I will put a 2 here. All right. It's not right there. Okay, I'll put a 2 there, right? And then that 2 affects the hydrogen, right? So basically, because I have 2 here, and now I have 4 on this side, I'll put a 2 here. And therefore, that's how you balance the equation. So that is something, again, you guys should be familiar with. So let me just skip all this here and move on to just some guidelines. I'm going to go through this quickly. If an element is present in just one compound on each side of the equation, try balancing that element first. So these are just some tips that would help you in terms of mastering the skills of balancing equations. Balance any reactants or products that exist as the free elements last. And in some reactions, certain groupings of atoms, namely polyatomic ions, remain unchanged. So in such cases, we treat these groupings as a unit. At times, an equation can be balanced by first using a fractional coefficient, and then the fraction is cleared by multiplying each coefficient by a common factor. All right, so those are just some hints involved in balancing equations. So let's do these exercises starting with the first one. How would you balance the first equation?
Could you add 2 to the FE?
Hmm?
Could you add like 2 in front of the iron?
Mm-hmm.
And then that would give you that balance to the other equation, but then wouldn't you add? You could add 2 to the other equation, and then you could have,
Here?
yeah, 2 there, and then with the O2, you could add a 3. That
Mhm.
would be their balance.
Not quite. There's one more thing you need to do. Because now you have 4 irons here.
Yes,
So how would you balance the irons?
you'd actually have to make it 4.
Exactly. So you change this to 4. And now the equation is balanced. All right. Very good. Okay, what about the next one? Well,
Put a 2 in front of the C2H6,
okay, put a 2 here.
yes, and then a 7 in front of the O2,
Mm-hmm.
and a 4 in front of the CO2,
Mm-hmm.
6, H2.
Okay. And I think that is indeed correct. Yep. Now let me just show you stepwise what I would do. Just in case this might help. So what I would do is I would start off with the carbons. I have 2 here, I have 1 here, so I'll put a 2 here. And then with the hydrogens, I have 6 here, I have 2 here, I'll put a 3 here. And then now we get to the oxygens, right? And you'll notice that I have 2 oxygens here. And on the right side, I have a total of 4, 2 times 2, 4, plus 3, 7. So the question now becomes how to balance oxygen. And this is where the fractional coefficient comes into play that was mentioned in the previous slide. I would multiply this by 7 over 2, because 7 over 2 times 2 gives you 7 oxygens, which balances with the 7 oxygens on the right. However, I will not leave that as a final answer because we need to clear this fraction. And the way I would do that is that I will multiply the entire equation by 2. So when I do that, I'm going to end up with 2 C2H6 plus 7O2 to give 4 CO2 plus 6H2. So that's basically how I would do that. All right. Okay, the last equation. How would you balance that one? Well,
Put a 3 in front of the NaCN.
okay, 3 in front of the NaCN.
And
Mhm.
then a 3 in front of the H's.
And a 3 here. And that is indeed correct. All right. So that's it. And there'll be some more balancing problems in the assignment that you guys have. Okay, let me move on now. Any questions about this? Any questions? Okay, let me move on now to a discussion of stoichiometry, right? So stoichiometry is basically that area in chemistry which deals with the quantitative relationships between different substances in a reaction. And of course, in order for us to determine that, there are a couple of things that we're going to need. I would say probably the most important and the first thing that you're going to need is a balanced equation, right? And that's the reason why we went through the exercises a while ago. If you don't have a balanced equation, pretty much any calculation based on that will be erroneous at best, all right? Now, the balanced equation is important because what is essential for solving stoichiometric problems is what we call a stoichiometric factor or mole ratio, right? And this is basically a fraction which relates any two substances in a reaction based on the balanced equation for that reaction, all right? So for example, if you look at this reaction, the reaction between carbon monoxide and water, right? It's balanced, and you see that there's a coefficient of 1 for the carbon monoxide, a coefficient of 2 for the hydrogen, and a coefficient of 1 for the methanol on this side. So basically, based on this balanced equation, we can come to the conclusion that there are some equivalences that exist between any two substances. So for example, between the carbon monoxide and the hydrogen, that's a 1 to 2 mole ratio, right? So 1 mole of carbon monoxide is stoichiometrically equivalent to 2 moles of hydrogen. We can also do the same when we look at the relationship between carbon monoxide and methanol. 1 mole of carbon monoxide is equivalent to 1 mole of methanol. And we can also do the same when it comes to the relationship between hydrogen and methanol. There's a 2 to 1 mole ratio between those two, right? And these ratios can be expressed as fractions, as you can see here. And these fractions become important when we're doing calculations. So the relationship, for example, between the carbon monoxide and hydrogen can be expressed as this fraction, where we have 1 mole of carbon monoxide as a numerator and 2 moles of hydrogen as a denominator. Or you can have it flipped around, right? You could have the 2 moles of hydrogen above and 1 mole of carbon monoxide below. And here we have other relationships based on the mole ratio between any two substances in the balanced equation, right? So these are very important, and this underscores the importance of having a balanced equation to begin with. You must have a balanced equation. The equation is not balanced, then you probably will end up with the wrong mole ratio, and that could affect your calculations subsequently. Okay, so when it comes to stoichiometric reactions or stoichiometric calculations, it really comes down to what you see here on the screen. Basically, you're converting the moles of one substance to the moles of another substance based on the mole ratio, which is based on the coefficients of the substances in a balanced equation. Now, you may have some calculations that you need to do in order to get the moles of, let's say, substance A, and you may have some subsequent calculations after you get the moles of the other substance. You may be asked to determine things like mass, volume, whatever. It all depends on how the question is worded. So, of course, we're going to start from the simple and then move on to the more complex. And the next slide is a very simple example. They gave us the balanced equation. And by the way, when it comes to these questions, I always tell my students, check to make sure that the equation is balanced if you're given a balanced equation, right? So this equation is balanced. And the question says when 0.105 moles of propane, which is the C3H8, this is propane, all right, is burned in an excess of oxygen. How many moles of oxygen are consumed? And it says that the reaction is that, right? So what I would do is start off with a 0.105 moles of propane, C3H8. And the question is asking how many moles of oxygen is consumed. So I start off with what is given, 0.105 moles of C3H8. And the question now becomes, what's the conversion factor that I'm going to use to convert from moles of propane to moles of oxygen. And the answer lies, of course, in the coefficients for the oxygen here and the propane here, which is assumed to be 1. So therefore, we're going to put 5 moles of oxygen as the numerator and 1 mole of propane as the denominator. And of course, we have to arrange the conversion factor like this so that we can cancel out the moles of propane unit, and you end up with, in the final answer, the moles of oxygen, which is what the question is asking for. So all we have to do now is multiply 0.105 by 5, and according to my calculation, that works out to be equal to 0.525 moles of oxygen. And that's how you do that. So that's a relatively simple example because it's a simple mole-to-mole calculation or conversion. All right? Any questions? Any questions? All right. So on to something more complex. So you could be given a question where, let's say, assuming that you have a balanced equation, you're given a mass of one substance and you're asked to determine, based on the balanced equation, the mass of another substance involved in the reaction. So what you'd have to do is do some conversion from mass to grams or mass in grams to moles, right? So let's say you're given a mass of a substance A expressed in grams. Then what you'd have to do is convert to moles, and this is how you do it. You'd have to divide by the molar mass of that substance, and that gives you the moles of that substance. And then you're going to use the mole ratio based on the coefficients in the balanced equation between B and A to convert from moles of substance A to moles of the other substance B, right? And then, depending on how the question is worded, if the question is asking for the mass of B, then you have to take it one more step. You have to multiply the moles of substance B by the molar mass, and that will give you what the question is asking for. So it all depends on what you're being asked. But the important point, and I'm going to stress this again, the important part of this calculation is right here. And this again underscores, and I can't say this enough, underscores the importance of having a balanced equation. So I always tell my students, before you do any stoichiometric problem, make sure the equation is balanced. If the equation is not balanced, then you need to balance it because any subsequent calculations based on an unbalanced equation will more than likely be incorrect. All right. Hold on, let me see here. So this is actually a question about, okay, so let's say you're given a question right here. Let's say you're given a question where you're given the moles of substance A. Do we need to convert moles of substance A to grams? And the answer is no. Because once you get the moles of substance A, then all you have to do is use the mole ratio to get the moles of substance B. All right? So that's an important point being made here because sometimes students make things more complicated than they should be. If they're given the moles of one substance, then they're thinking, okay, maybe I need to convert from moles to grams. You don't need to do that because remember the equation gives you the mole relationship between substances. So if the question gives you the moles of one substance to solve a problem like this, that makes your life a bit easier compared to if the question was given, if it gave you the grams. If the question gave you grams, then you'd have to convert to moles. Then you'd have to use the mole ratio and then do whatever to solve the problem. All right? Okay, so some examples. So let's look at this question here. Now, in this case, they did not give you the equation, so you have to figure out the equation, all right, based on the information provided. The question says, the final step in the production of nitric acid involves the reaction of nitrogen dioxide with water. And it also says that nitrogen monoxide is also produced. So the question is asking, how many grams of nitric acid are produced for every 100.0 grams of NO2 that reacts, all right? So firstly, we have to figure out the equation, right? So the way we're going to do that is that first we figure out what the reactants are and what the products are, right? And then write the formulas for them, write the unbalanced equation, and then we have to balance it. Okay, so I want you to look at the question, and I want you to tell me, based on the information provided, what are the reactants in this reaction?
Nitrogen dioxide, water.
Exactly. So NO2 plus H2O. Okay, and what are the products? Again, based on the information provided.
Nitric acid.
Nitric acid, the formula for which is HNO3 and what?
monoxide.
and O, all right? So now that we have the unbalanced equation, now we have to balance it, right? So how would you go about balancing this equation?
A 2 on the nitric acid, a 2 on the nitrogen monoxide, and a 4 on the nitrogen dioxide.
Hold on, a two on the what? Nitrogen monoxide or dioxide?
Monoxide, and then a 4 on the nitrogen dioxide.
Okay, let's see if this works. So four nitrogens, 4 twos 8, plus 1 9, 2 3 6, plus 2. Okay, that won't work because we have 8 oxygens plus 1 9. On the right side, we have 6 plus 1, 6 plus 2 8. So yeah, something is wrong here. Let me erase these again. Okay, so what do you have for me now?
You need a 6 on the nitrogen dioxide.
Hold on 1 minute. Okay, so 6. Whoa, that's a huge number. You sure about that?
Oh, it could be 3. Oh, okay. Okay. 3 on the nitrogen dioxide and 2.
Wait, hold on 1 minute. Hold on 1 minute. This thing is saying that my sharing has paused. I don't know what that means. I've never seen this before. So let me okay. All right,
3 on the
so
nitric acid, oxide. Nitrogen.
so you're saying 3 here?
Yes.
Whoops. Okay, so you're saying 3 here,
And then 2 on the nitric acid.
2 here,
Yes.
and that's it?
Yes.
Okay, so 3 nitrogens, 2 plus 1, 3, okay. 6 plus 1, 7, 2, 3, 6 plus 1, 7. And we have 2 high. Okay, so now the equation is balanced. Very good. All right, so of course, that's important. That's the first thing we should do. So what I'm going to do now, since I'm going to need space, I'm going to take this over here and lock this here and go back to Word and get rid of this here. No. Get rid of all this here. So this is the reason why I prefer to use my laptop, because I have some special drawing applications, which, anyway, all right. Let me bring. Okay, so the question says, now, okay, let me rewrite the equation that you just gave me. So the equation is, the balance equation is 3NO2 plus H2O to give 2HNO3 plus NO. All right. So the question says, how many grams of nitric acid are produced for every 100 grams of nitrogen dioxide? So they gave you 100.0 grams of NO2, and they're asking for the mass in grams of HNO3, all right? So basically what you'd have to do is first convert from grams of NO2 to moles of NO2, and then using the mole ratio, you're going to convert moles of NO2 to moles of HNO3, and then using the molar mass of HNO3, you convert that to grams of HNO3, all right? So basically, we're using a series of 3 conversion factors or mole ratios to get from the grams of NO2 to what the question is asking for, which is the grams of HNO3. So I'm going to start off with the 100.0 grams of NO2, and we have to convert that to moles. So that would be 1 mole of NO2 above, and the molar mass of NO2, we have to calculate that based on the periodic table values for the molar masses. So nitrogen is 14.01 plus 2 times 16, which is 32. So the molar mass of NO2 is 46.01 grams for every 1 mole, all right? Then the next conversion factor will be the mole ratio between the HNO3 and the NO2. And that's why we have a balanced equation, because we can see that the coefficient for the nitric acid is 2, and that for the NO2 is 3. So the way we represent it here in the next conversion factor is that we're going to have 2 moles of HNO3 above as the numerator, and 3 moles of NO2 below as the denominator, all right? So far, the grams of NO2 will cancel out, the moles of NO2 will cancel out, so we are left with, here, up to this point, the moles of HNO3. But there's one more step to go, and that step is to go from moles of nitric acid to grams of nitric acid. So we need another conversion factor where we will put 1 mole of HNO3 down below as the denominator, and the numerator would be the molar mass, which we can calculate. So for oxygen, that's 3 times 16, plus for nitrogen, that's 14.01, plus for hydrogen, that's 1.008. So according to my calculations, this gives you 63.02 grams of HNO3. And then we do the number crunching. So 100 divided by 46.01 times 2 divided by 3 times 63.02. And according to my calculations, this works out to be equal to 91.463. So 91.31 grams of HNO3. And that's how that is done. All right. Any questions? Any questions? All right. The next one, again, you're not given an equation. You're given information based on which you're going to write down the equation. So that will be the first thing we need to do. And then it says, okay, gives you the percentage of sulfuric acid, which is one of the reactants. It gives you the density of that solution. And it's asking how many mils of this solution are required to convert 1.00 kilograms of ammonia to ammonium sulfate. Okay, so based on the information provided, what would you say is, what are the reactants and what are the products? Let's start off there. Whoops, sorry. Okay, and then I do this. Okay, so what, based on the information provided in the question, I'm going to write the equation up here. What would be the reactants and what would be the products and their formulas? it says ammonium sulfate is produced commercially by passing gaseous ammonia into aqueous solution of 65% sulfuric acid. So what would be, based on that information, what would be the reactants and what would be the product?
Gaseous ammonia,
Okay, so ammonia
H2SO4.
and H2SO4. Okay, and what would be the product? Ammonium sulfate, for which the formula is NH4, 2SO4. Okay, very good. So now we need to balance this. So how would you balance this? Exactly, that's it. All right. So now that we have the balance equation, we can move on to the calculation part of it. So let me take this over here. And there must be a way to just, oh. All right, okay, so I'm going to rewrite the same equation up top here, which is what's going on? Okay, which would be 2NH3 plus H2SO4 to form NH4, 2SO4. All right, so that's the equation we're working with. So the question says that they gave you 1.00 grams of, 1.00 kilograms of the ammonia solution. All right. And the question is asking for the milliliters of H2SO4 that will react with it. Okay. Now, couple other things you're given. You're given that the percentage of the H2SO4 is 65%. And you're also given that the density of the H2SO4 solution is equal to 1.55 grams per mil. All right. So that's basically what you're given. So what I would do is start off with the 1.00 kilograms of ammonia solution. So this is a solution, all right? Now, what I would do is, let me see how I'll tackle this. What I would do is, actually, no, it's not ammonia solution, just simply ammonia gas. My bad. What am I saying? Yes, it's ammonia gas. Okay, so ammonia gas, right? Okay, so what I would do first is convert this to grams, all right? So, of course, that would mean that I would multiply by 1 kilogram of ammonia down here and 1,000 grams of ammonia above, right? Then I will convert that to moles, right? So I'm going to put 1 mole of ammonia above as a numerator, and down here the molar mass of ammonia, which would be 14.01, 14.01 plus 3 times 1.008. So according to my calculation, this works out to be 17.03 grams of ammonia. All right. So that goes with that. That goes with that. Okay. Now, the next step is the mole ratio between the ammonia and the sulfuric acid. And that's where the equation comes in. Based on the equation, there's a 2-to-1 ratio between the sulfuric acid and the ammonia. So I'm going to put 2 moles of NH3 down here and 1 mole of H2SO4 above. All right. So this will cancel out with this. All right. And then the next step is I would find the mass of sulfuric acid. So I'd convert from moles of sulfuric acid to mass. I'm going to put 1 mole of H2SO4. I'm going to need more space. So the molar mass of sulfuric acid is, okay, so 4 times 16 plus 32.07 plus 2 times 1.008. So according to my calculation, that's 98.09 grams of H2SO4. Oh Lord, okay, let me continue down here. Now the next step is, because remember, the aim is to find out the volume of the sulfuric acid solution. Up to this point, we would have determined the mass of the sulfuric acid solution. Now, according to the question, 65% of the solution by mass is sulfuric acid. So what does that mean? That means that for every 100 grams of the solution, 65 grams of it would be H2SO4. All right? So this unit will cancel out with this right here. And then the next step is to find out the volume. And according to the question, the density of the solution is 1.55 grams per mil. So the way I would represent that here is that I'll put 1.55 grams down here of the solution, and above I'll put 1 mil of the solution. So that's basically the string of conversion factors you're going to need in order to do this calculation. So let me do the number crunching. 1,000 divided by 17.03 divided by 2 times 98.09 times 100 divided by 65 divided by 1.55. So the answer I get now, rounded off to 3 sig figs, is going to be equal to 2,860 milliliters. So that's the answer I got. All right. Any questions about this? Any questions? Okay. So let's move on. Oh, let me bring this over first. Okay, I guess this will have to be the last topic for today, limiting reactants. Now, very often, and this is in practice, in order for a reaction to take place, even though you might have the correct information about the balance equation and all that, very often in practice, in order for the reaction to actually take place, we have to ensure that at least one of the reactants is in excess. In other words, instead of being stoichiometrically equivalent in terms of the amounts, we basically use a high, relatively speaking, amount of a particular reactant. And therefore, the other one would be more limited, all right? So as a result of that arrangement, what will happen is that the reactant that is limiting is the one that will basically be completely consumed. And at the end of the reaction, you're going to end up with an excess of the other reactants, right? So as stated here, the reactant that is completely consumed is the one that limits the amount of products that you end up with. So therefore, we call that reactant the limiting reactant, all right? Key thing you need to understand about this, however, is that the limiting reactant is not necessarily the one that is present in the smallest amount. And I think we might see 1 or 2 examples of that. So let's look at an example, which is not a chemistry example, but let's say you're given the task of preparing packaged meals, right? And we come to the conclusion that we work with this formula here, right? One sandwich plus 2 cookies plus an orange gives you a meal, all right? Now, let's say, so that's the formula we're working with. Now, let's say at hand, we have 10 sandwiches, 18 cookies, and 12 oranges. The question is, how many packaged meals can you make, all right? Now, let's say we look at things from the standpoint of the sandwiches, right? If you have 10 sandwiches here, right? If this is 10 here, then the number of cookies based on this ratio here that you're going to need will be 20 cookies, right? But we do not have 20 cookies, we have 18 cookies, right? So therefore, we cannot use the sandwiches to determine how much of the packaged meals you're going to get because you simply do not have enough cookies. On the other hand, let's say you have 12 oranges, right? If you're starting off with 12 oranges, right, you're going to need 24 cookies. Again, that won't result in you making any prediction about what the number of packaged meals will be because you don't have enough cookies to use up all the 12 oranges. Now, if we look at things from the standpoint of the cookies, right? According to the information here, we have 18 cookies, right? So if you look at things from the standpoint of the 18 cookies, well, based on this formula here, that means that the number of sandwiches that you're going to need will be 9, and the number of oranges that you're going to need would be 9 as well. Turns out that, okay, we have 10 sandwiches, so therefore we can use up 9 of the 10 sandwiches, so 1 will be left over. And based on the 18 cookies, we're going to need 9 oranges. We have 12, so that means that 3 will be left over. So therefore, it will be the 18 cookies that determine how many packaged meals you're going to end up with. And therefore, because there's a 2-to-1 ratio between those two, we can say that the number of packaged meals that you can manufacture will be 9. But the key thing is you have to remember that you're going to have some oranges left over, 3 oranges left over, and over here, you're going to have 1 sandwich left over, right? So what does that mean? That means that the cookies are the limiting item, and the oranges and the sandwiches, or the 1 sandwich, would be the excess items, all right? So this is basically the whole idea behind the limiting reactant concept when it comes to chemical reactions, even though we are applying it to something which is not chemistry related. So we're going to move from this, and this will have to be the last thing I'm going to talk about, to an actual chemical reaction where we can apply what we have just learned. So in this case, we're looking at this equation here, the reaction between C2H4 plus Br2 to give C2H4Br2. All right, that's the reaction. Now, this is simplified because there's a 1-to-1 mole ratio between these two, right? So basically, for every 1 molecule of C2H4, it's going to react with 1 molecule of bromine, and we can also apply that at the molar level. So in this particular example, what they have done is that they have used 28 grams of the C2H4, which is, by the way, called ethylene, right? So 28 grams of ethylene is equal to 1.0 moles, right? And then it's going to react with 128 grams of bromine, which is equal to 0.80 moles, right? So basically, we can easily tell which one is limiting because it's a 1-to-1 ratio between these two, and we have less of this than this. So what does that mean? That means that all of this will be used up. So the change here will be minus 0.80 moles. All of this will be, well, not all of it, but 0.8 moles of this will be used up, right? So therefore, there'll be no bromine left. So there'll be 0 moles of bromine. But here, you're going to have 0.20 moles of C2H4. So that means that the bromine here is limiting. Bromine is a limiting reactant, and the ethylene will be the excess reactant. And therefore, it is the bromine being a limiting reactant that will determine how much product you're going to end up with. And because it's a 1-to-1 mole ratio between the bromine and the ethylene dibromide, which is what this is, we can predict that the moles of this produced will be 0.80 moles of C2H4Br2. So this is the amount of that produced. All right, so basically that's what happens now. So I think we answered question number 1 in the explanation here. The question is asking here, what is the mass of the ethylene that is left over? Well, that's very easy. All we have to do is multiply the 0.20 moles by the molar mass, and that will give you the mass of the product or the reactant, the excess reactant. All right. So when it comes to solving limiting reactant problems, remember these are problems where you have at least 2 reactants involved, right? If there's only 1 reactant, then that reactant would be the limiting reactant. But in the case of other reactions where you have 2 or more reactants, you have the problem of determining the limiting reactants, right? One way to solve them is to perform a normal stoichiometric calculation of the amount obtained starting with each reactant. And then, based on what your calculation gives, the one that produces the smallest amount of reactant is the limiting reactant. Okay, so we're going to stop here. And then next class, we're going to look at an example of this. But before you leave, let me just say that I think you should have seen by now that I've graded, what did I grade? I think I graded assignment 1. And I'm going to grade, wait, did you guys turn in assignment 2 already? Okay, so I have to grade that as well. So I'm going to aim for today in terms of sending you by email your graded work. And the reason why that's important because next week will be you'll be giving your first test. So I'm going to schedule that test for Thursday of next week. So I'm going to send you your graded work. I'm going to also post in Canvas the answer keys to those assignments so that you can have that to review in preparation for your test. I'm still on the fence about the chapters covered. Definitely chapters 1 and 2. But I'm not sure about 3 yet, which is what we're working on. So I'll let you know. I'll definitely let you know by Thursday. All right. So see you guys Thursday. Yes, sir.
Much happened.
Oh,
I
okay.
hit it on Thursday.
Okay, all right.
Have a good day.
You too. Hello. Okay, let's get out.